Okay, so Calc 1 students, we're going to look at a typical optimization problem that has to do with area of a rectangular plot enclosed by a fence. Okay, a typical, very famous calculus problem for Calc 1. All right, so the idea on this is you have a three-sided fence. It's built next to a section of a river, so that forms the border, so you're not going to put a fence by the river. And then you have, the key thing is it says you have 96 feet of fencing available, and we're going to find the maximum enclosed area and the dimensions of the corresponding enclosure. So what I was trying to show on these pictures here is, well, you could stretch it out. You could have like kind of a long, skinny, rectangular region like this and use your 96 feet of fence there. You could make it kind of long and skinny this way, or you might make it more condensed, like almost like a square or something. So you're trying to figure out what would maximize the amount of area that would be contained in that enclosure. So what you typically do on these type of problems is the first thing you want to do is just, list your variables, maybe draw a picture. I'm just going to draw a little picture here. So we've got the river, we got our 3 feet of fence, and I'll just use what we got here. I'm just going to say X and Y. It's rectangular, so the opposite sides are going to be the same. So we're going to make an equation for the perimeter. So the perimeter, of course, just means add the sides. You got 3 sides, so you would have X plus Y. So that would just be 2X plus Y. And of course, the problem tells you that that perimeter is 96 feet. So the first thing that you come up with is you have that type of, you have the equation. That's not the one that you optimize and work with the derivative on, but that's an important part of the problem. Okay, now when you're doing these optimization problems, whatever you're optimizing is going to be the function that you create in one variable that you're going to differentiate, find critical points, and that kind of thing, okay? So after we get that perimeter function, now we move on and we're going to kind of come up with a area function in terms of one variable. The key thing is you have to make sure your function ultimately has one variable in it. Okay, so to begin with, we'll just call this the area. The area is just going to be equal to X times Y. Okay, it's base times height. Right now, this is in 2 variables. You haven't seen this kind of function notation, but you'll see this in a Calc 3 class. A of x, y, if your function has 2 variables, it's written like that. So what we have to do is we have to trim it down to 1 variable. So we're going to work with the perimeter equation. So basically just solve for either variable. It doesn't make any difference which. To me, it's just as easy to slide the 2x over to the right side. So you would get y equals 96 minus 2x. Okay, so here's y. Let's plug in this thing into it, like that. And then we'll have a function that's in terms of 1 variable x. So now this is going to become a of x. It's got 1 variable, bring down the x. The y gets replaced with 96 minus 2x. Okay, and there's our function. Okay, and I'm going to go ahead and multiply it out, and then we'll work with differentiation and optimization here. Okay, so always get the function that you're going to optimize in terms of 1 variable. All right, now we move on. Kind of the third key step is where we start getting into the calculus. We want to go ahead and do a prime of x. So that's going to be 96 minus 4x. Okay, of course, we find a critical number. And the critical number, we're just going to set that equal to 0, find out where the derivative is 0. That's a simple equation to solve. Move the 4x to the other side. And then divide by 4, like that. So that'll be 24. So x is equal to 24. All right. Now there's a couple of things that you can do on this problem. You can treat it a couple of different ways. So x is 24. You can do, I think I'll go ahead and just show you what we call the second derivative test. And the second derivative test is used to verify that that 24 is going to provide a maximum. So what you do on that is the second derivative, okay, your first derivative is 96 minus 4x, so the second derivative is negative 4. And what that means then is if you think about how a second derivative relates to concavity and points of inflection, I usually tell students to remember the second derivative test this way. If the second derivative is negative, then it means that you're concave down, and you can kind of think of this as being a maximum. This is really a visual tool to help you remember. The second derivative basically says if the second derivative is less than 0, then you have a max. Okay, so we would have a max at 24. If the second derivative was positive, then you would have a minimum. Okay, so we know we have a max. That's a kind of a quick way to verify that you have a maximum then. Okay, fifth thing we're going to do is we just go back to our diagram and then we'll wrap it all up here. So our diagram, we had the river. We just figured out that we have 24 feet here and 24 feet here. So we got to figure out what y is now. Well, okay, a couple of ways to do this. Basically, all of the fencing adds up to 96. So if you just subtract 24 from that, then I think that'll give you 48 feet. All right, so you end up having this then. All right, now we can draw our conclusion on this problem. So basically, the area is maximized if the dimensions are 24 feet by 48 feet, okay? And then the area on this is going to be, we know the area is just x times y, so that would be 24 times 48. Get my calculator out on that. So let's do that, and that'll give us the maximum area then. Okay, so 24 times 48 is going to give me 1,152 square feet. All right, so this is what you get as your answer to the problem. These are the dimensions, and that's the maximum area. Okay? All right, one thing that you can also do on this that's worth doing, I think, is you could go back and look at your first derivative, which is this, and you can even look at your function too. Let's just graph the function. Not the first derivative. Let's graph the function. So we got 96x, and then minus 2x to the second. That's the function that we differentiated. And for a window, let's see. Well, we probably got to go up at least to about 48. So I think what I'm going to do on this is go 0 to 50, like that, maybe scale by 10. The maximum area was 1152, so I'm going to go 0 to, like, say 1200, and maybe scale that by, let's just scale it by 100, I guess. So we could do that, and when we graph this, you'll see a maximum there. So basically what you can do on this too, a way that you can use technology to verify this, is once you get your area function in there, you can go second calc, and then you can go to option 4, which is a maximum. You get a left bound, so you move the cursor so it's a little bit to the left of where you can visually tell the max is. Okay, you got a boundary. You get a right bound, move to the right of the maximum. Okay, that, when it says guess, press enter, and out will pop the 24. Okay, the calculator doesn't do a derivative, it does numerical methods, so it's not exact. So for all practical purposes, you can say, okay, we got 24 when we set the derivative equal to 0, and there's your maximum right there. Okay, another worthwhile thing to do, just to make some simple connections, is if I graphed the derivative, 96 minus 4x, let me kind of show you what this derivative looks like. Well, that derivative, what's going on that is it's basically the value of your derivative is positive here because the function's increasing. But right here, where you have a maximum, the value of that derivative is 0. and then the value of the derivative will end up being negative. So if you went through and maybe made the y minimum like negative 200, you'll see this a little bit better. So basically you have a positive derivative because the function's increasing, zero derivative, that's a critical point. The value of that derivative is 0. It's on the x-axis. And then the function decreases, so notice your derivative's negative. Okay? All right, so those are all good connections to make. So that's how you handle the famous, world-famous calculus problem with a fence. So the maximum enclosed area is 1152. And the dimensions we came up with were 24 feet by 48 feet. All right, hope you enjoyed. Thanks for watching.